Thank you very much for joining our session today. We hope you're all keeping safe and well. Welcome to the latest session in our Siemon TechTalk series. My name is Christopher Homewood, Marketing Manager for Europe, Russia and Central Asia at the Siemon Company, and I'm excited to be joined today by my colleague Alberto Zucchinali, Siemon's DC Services and Solutions Manager for Europe. In today's session, Alberto will explore Wi-Fi 6 and 6E and examine the technologies that are available to you today, as well as the approaches, topologies and cabling considerations you need to be aware of to prepare for and successfully deploy next generation Wi-Fi within your organizations. If you have any questions during the session, please enter them into the panel provided on the right hand side, and we will have a short Q&A discussion at the end to address them. Now, Alberto, over to you.
Many thanks, Chris, and thanks everyone. Hello and welcome to our Tech Talk about next generation of Wi-Fi. We can say that with the increased use of mobile devices, Wi-Fi is now everywhere, with a large adoption across all types of facilities. One of the main solutions to meet the increasing demand for mobility and flexibility has been the adoption of Wi-Fi networks. With this technology update, we hope you will have the keys to evaluate and consider the associated aspects of a physical layer to properly design this latest Wi-Fi standard applications. As for wired Ethernet applications, to support traffic demand, the speeds are increasing. And between the first old generation of Wi-Fi running at 11 megabits per second and today's Wi-Fi 6, there is a big gap. We progressed up to 450 megs with Wi-Fi 4, and we are now approaching 10G with Wi-Fi 6. The aim is to support everything. From mission-critical business applications to streaming of ultra-high definition video. So these are the four key topics in our agenda today. We will have an overview of the latest technologies, and we will cover what a designer or installer or consultant should be aware of to implement a future-proof infrastructure for next-generation Wi-Fi. So what are the alternatives to connect the access point to the physical network, either for indoor or outdoor installation? There are actually a number of reasons to consider the latest generation of Wi-Fi devices. We can mention higher data rates with peak gigabit speeds, increased capacity with reduced latency to support higher number of users and devices, lower power consumption, and in this case, this includes also low battery consumptions for smartphones and so on, and mobile devices, which are supported by Wi-Fi 6 networks. The increased efficiency and lower latency, this is another benefit, and some robust outdoor network operations. Everybody knows the old protocols like 802.11b/A and G. They are now renamed by the Wi-Fi Alliance as a Wi-Fi 1, 2, and 3. The scope here was actually to simplify all the references and making them easier to remember. In 2009, we had 802.11n, which is called now Wi-Fi 4, with speed up to 600 megabits per second. We have actually to remember that the actual wireless speeds vary significantly from the shown theoretical maximum speeds due to some elements. First of all, distance, the distance from the access points, as well as any physical obstacle or walls or any signal blocking material will affect the propagation of the signal and will reduce the speed. Interferences, so the presence of other wireless networks and devices in the same frequency range and in the same area, will have an impact on performances. And the fact that bandwidth in this case is shared. So the available bandwidth is shared between all users on the same wireless network. With the publication of Wi-Fi 5, which is called in the standards as 802.11ac, we started advising our customers to specify category 6A cabling in combination with link aggregation to ensure immediate support of the bandwidth, which was actually the speed which was available at that time, which was up to 1.3 gigabits. That data rate imposed to evaluate the option of something more than one outlet, because one outlet in Cat6 was not sufficient anymore, up to only 1 gigabit. The new Wi-Fi 6 is the latest generation we see on the market. It's built on the strengths of Wi-Fi 5 by adding efficiency, flexibility, and scalability, and so allowing for some increased speed and capacity for all the next generation applications we can see on the horizon. So 4K, 8K video, high density or high definition collaboration apps, all wireless offices, Internet of Things. Here you can see at the top of the slide that we have a Wi-Fi 6E as well. Wi-Fi 6E is not a new wireless protocol. It's actually an expansion, or we can call it a second wave of a Wi-Fi 6 technology into a new and much wider radio frequency range. And this will be a matter of a later discussion. I mean, I'll discuss the topic a bit later. But we are not over. The next step is already there. IEEE has already begun to develop Wi-Fi 7. And in this case, this new technology will support the development of extremely sophisticated technologies such as ultra high quality videos or high resolution virtual reality, augmented reality. So we are really now ready for the next gen. So now we can have a deeper view on the technical parameters, and you can see how Wi-Fi 5 and 6 could achieve higher levels of performances. We can just start having a look at the basic things, the basic concepts. You can see here that connectivity needed by different applications will change. So for Wi-Fi 5 and 6, we needed 2 connections with a minimum of category 6A. This is due to the required speed of the fixed part, what we can call some way the access point uplinks. And for Wi-Fi 6, you have definitely to forget about the old cabling system, as we need a higher data rate. Wi-Fi can achieve a theoretical data rate of 9.6 gigabit per second when all of the available 8 spatial streams are adopted. Just to clarify, spatial streams correspond to the technology that transmits over multiple send and receive antennas. what's called a MIMO technology. In that sense, the access points involved in this technology have typically 3 or more antennas. MIMO helps improve performances by sending data in a focused signal much more directly at the connected clients rather than over a broad spectrum. So we mentioned Wi-Fi 6E. This is just an evolution of Wi-Fi 6, but the important thing is that they extend operation in the 6 gigahertz frequency range, in addition to the usual existing 2.4 gigahertz and 5 gigahertz spectrum. This will allow to use wider transmission channels. While 80 megahertz and 160 megahertz transmission channels have historically been allowed and permitted for higher data speeds, in practice, those wider channels were rarely deployed just because of limited availability. Now, this enhanced capability of Wi-Fi 6E will reduce latency, and the key point again is that we cannot expect any previously existing Wi-Fi device competing for bandwidth in this newly open spectrum. And in the same manner, transmission speeds, even when obstructions are present, will improve in an important way. This will open, as an example, a much better experience with augmented reality glasses. In April 2020, in the US, the FCC ratified a report to allocate 1.2 gigahertz of unlicensed spectrum in the 6 gigahertz bandwidth just for Wi-Fi use. The situation in Europe is slightly different. The European Commission is expected to rule on 6 gigahertz in early 2021. We expect to have an available bandwidth in the range of 5925 to 6425 megahertz for the use of low power indoor and very low power devices, so for IoT as well. The term Wi-Fi 6E was introduced by Wi-Fi Alliance to identify and certify the Wi-Fi devices that can support this new band. So in a nutshell, this new technology opens an additional area, a free and open highway for Wi-Fi. This fact is significant for a couple of reasons, or just saying it's the first addition to consumer wireless frequencies in 20 years. This step increases the amount of spectrum available for Wi-Fi, adding between 75 and 200% to the previous 600 megahertz bandwidth or spectrum. Because it's an unlicensed spectrum, its use is not restricted to a single company or geography in the way that 5G is, for example. As a result, it's open to multiple uses by different users throughout any country. And now, related to cabling, what's the importance of a proper structural cabling solution for support of Wi-Fi? Wi-Fi 6 access points need, as I said, two class EA, category 6A or higher connections. The access points will need at least one class E or Cat 6A connection to support either 2.5 or 5 gig transmission speeds, But to take a full advantage of Wi-Fi 6 and then greater speeds than 5 gigs, 2 connections will be required to support link aggregation. Even at the backbone level, there are some recommended minimum speed. So a minimum of 25 gigabits per second multimode optical fiber backbone is considered to be a must to support Wi-Fi 6 uplink capacity. In fact, this is already a key recommendation for Wi-Fi 5 implementation. Wi-Fi 6 access points will also need more power and will need a thermally stable shielded cabling system. Just because the radio chips are required to do much more complex signal processing, it's expected they will be unable to work with a 13 watts budget of power over Ethernet type 1. And so they will require very probably type 2 PoE up to 30 watts. Since the higher power level can cause some heat buildup in cable bundles, Wi-Fi 6 access points will be definitely better supported by some thermally stable shielded cabling systems and some solid conductor cords. In this case, we have to remember that Siemon solutions in that field are qualified for mechanical reliability up to 75 degrees. So still in the cabling world, just a quick summary, Cat6a as a minimum with a PoE support, minimum of 25 gig for the backbone. So in this case, fiber backbones will be needed. But anyway, if you don't expect to install the latest Wi-Fi 6 or 6E right now, even in that case, you should design a flexible cabling infrastructure that can accommodate the addition of future access points and enable a quick reconfiguration of coverage areas. And this will definitely save time and money later on. So to allow for full flexibility and to give some room for upgrading, cabling design should be based on zone cabling grid. What are the cabling implications here? It's a matter of considering a standard-based zone cabling topology, which is done by using a service concentration point. The traditional way of calling that for structural cabling was consolidation point. From there, you can distribute service outlets with all of its benefits. This includes some fast and easy deployment of new devices via spare outlets. And this will help definitely to upgrade to Wi-Fi 6 with a higher data rate once required. Rapid reorganization and less disruptive moves, adds and changes by isolating them to the shorter cabling link between the CP, the consolidation point, or the service, the zone enclosure, and the service outlet or device. That will help conveniently combine outlets by serving access points and other intelligent building devices within the same consolidation point. So zone cabling is especially ideal for the deployment of grid-based Wi-Fi coverage areas. In this situation, the diameter of wireless coverage is larger than the square grid pattern to ensure reliable wireless transmission across a facility with no gaps between coverage areas. In emerging technologies like Wi-Fi 6, but even this is applicable to 5G, applications are already developed using what they call the enhanced reliability of the data rate. This could imply sometimes the reduction of the coverage area in certain cases, but while up to now we've been planning Wi-Fi considering floor layout and walls, now we will have to take in consideration as well the amount of connected devices, the required speed per device, and this will be the true difference between coverage and capacity. Reducing the coverage will enhance the capacity, and less connected clients will mean higher speed. So back to the physical layer topology to connect the access points to the LAN network. You can see here that Wi-Fi 4, for Wi-Fi 4, one port was enough to support the data rate, and Cat6 cabling was the good choice. Point-to-point topology was adopted, and typically adopted with the option of consolidation points in order to add flexibility to the cabling infrastructure for future move add-in changes. Nowadays, since Wi-Fi 5 and 6 appeared, 2 ports are recommended to support the data rate, and Cat6a cabling was the way to support 10G without any issue. Some access points still use only 1 port for Wi-Fi 5, but will not offer the full exploitation of the available speed. Even for those access points using 1 port for data only, they might use 1 port for out-of-band management systems, and some other already have a dedicated port for just PoE. So the question is, sometimes is there a way to simplify what we are used to in the traditional architecture? And the newest acronym in the structural cabling industry is MPTL. This acronym stands for Modular Plug Terminated Link and refers to terminating the equipment end of horizontal cable with a modular plug to connect directly into a device versus the traditional way of terminating at an outlet and connecting the device with a patch cord. This option will help intelligent building deployment, as it provides a new means of connection for the growing number of devices that converge on a unified network infrastructure. Installing a plug versus an outlet on the end of a horizontal cable and plugging directly into an end device is not really a new concept. Security camera installers have been doing this since IP cameras came into existence in late 1990s. The problem was that connecting directly to the device with a plug negated the standard definitions of a permanent link, which includes a horizontal cable from the patch panel to the equipment outlet, as well as the definition of a channel, which includes the permanent link plus patch cords on both ends. Nowadays, both the TIA and ISO define some documents which provide definitions for MPTL, for modular plug terminated links, and some examples of configurations. Those documents can provide also performance specifications for all classes, starting from the basic ones and going up to the equivalent of category 8. In this sense, the small dot you can see on the right side of the channel, so the MPTL actually solution that Siemon is promoting is called the Z plug. So an alternative way to the traditional installation is to use a Z plug that terminates directly to the solid cable and connects to the access point. A big advantage is the ease of deployment and full compatibility with PoE. Also, in case of, I would say, outdoor access points are required, we can see a few methods to connect them. In case the access point is directly installed outside the building, a first method could use outside plant cables out of a service outlet, so close to the wall, and terminate the cable with MPTL, so Z-plug, and a metal gland IP rated in order to protect the cable connection against temperature and humidity or dust. In that sense, outside plant cables are UV resistant and have a water blocking construction. A second method, when the environment is harsh, can see the use of some weatherproof conduits. Whenever the site's location is close to the sea or the ocean, as an example, you could have some salty air that can affect cable quicker, then this conduit could definitely help by keeping the cable totally protected. In case your access point is not next to the wall, you could think of using an outside cable on a longer distance. Just note that in this case, the CP, the consolidation point, should be next to the external wall, as an outdoor cable cannot run typically inside the building on a longer distance than 2 meters without protection. Depending on the configurations, you could terminate the cable with a ruggedized outlet, an IP-rated box, and some ruggedized cores. Should you have to mount the access point on a pole, a direct connection, so an MPTL approach, would help even more without any point of interruption or any disconnection between the link coming out from the building. Outdoor access points are often mounted nowhere near a local power source, but if in case local power cannot be provided or is not a cost-effective solution, you still might need a way to power your access point. So ideally, your access point will support power over Ethernet and will be able to draw DC power directly through the same copper cabling that connects it to the network. In that sense, a shielded twisted pair cabling will ensure low risks of interference and a lower temperature rise when power is applied over the cable. This will definitely help, and it could be a big concern whenever those installations are in direct sunlight and in warm climates. In extended distances, in situations, the access point will be connected via fiber optic cable, and that solution will definitely have no chance to deliver PoE. That's where a duplex fiber for data transmission along with power cable could be a solution. And then if the access point includes a fiber port for data, you could have a direct connection onto the access point from the fiber cable. Otherwise, you could terminate the fiber to a PoE media converter, which would be placed in an outdoor rated enclosure. And then this will convert the optical signals and deliver both data and PoE to the access point simply by using a copper patch cord. In all of this situation, of course, you will always have to consider the impact of lighting strikes. Then the outdoor access point should be properly grounded and to prevent any damage. And depending on location and side of the access point, you might need to ground them to the mounting structure, and the structure itself might need to be equipped with some specific protection. Most PoE-enabled outdoor access points feature some built-in dedicated surge protection to isolate and protect any inside network equipment. Then it will anyway be crucial and important to refer to your access point manufacturer's guidelines for grounding. Back to the MPTL termination and Z-plug, we have to mention that this is the most flexible plug that you can see, and you can use with shielded or unshielded, solid or stranded, indoor or outdoor cable. You can see here how the Z-plug field termination is easy and quick. This will take typically less than 1 minute. So fiber will be rounded up by this module, clipped, and the termination will be done. Z-plug is also one of the shortest plugs on the market, and that's robust for all PoE applications up to HD-based, so then up to 100 watts. In that sense, this will suitable not just for Wi-Fi, but also for a number of IP-enabled devices like audio-video or lighting or cameras. One of the questions we typically receive is how do you test an MPTL? That's a scheme. You can note here that the plug is connected to a patch cord adapter on the right side. It's possible to test an MPTL to TIA currently, and the question is it possible to do that in accordance to ISO or Senelec standards? And the short answer is not yet, but you definitely can make sure that your MPTL will perform the right way. The standard ISO 11801-9910 has reached now a stable draft phase and will likely be approved for publication before the end of the year. Then, for now, just make sure to select the MPTL setting under the TIA test limits on your tester, and definitely in a short time, equivalent ISO settings will be available as soon as standardized, and so that will be available in tester firmware updates. Then we can say that new Wi-Fi technologies will give you better performance, some reduced power consumption. They will support many exciting new features. There's definitely a way to simplify and optimize your networks for future needs in converged intelligent buildings by adopting new design and installation approach. And now more than ever, it's critical to have some best fit physical infrastructure. It's also crucial to refer to a trusted partner with the right expertise to support in this transition. So now, we can just strongly suggest you to plan your networks to use Wi-Fi 6 and its predictable performances for advanced applications such as high-resolution video, high density and high definition collaboration apps, all wireless offices, IoT. Then you have to make your best infrastructure choice to connect to your access point and really enjoy the new technology without suffering any traffic and transmission issue. And that was it for today. Thank you for your attention and your attendance. In case you have any additional questions, please add them into the panel you have on your right-hand side, and feel free. Feel free to ask, feel free to contact me at a later stage in case, and many thanks again for you to be there.
Brilliant, thank you, Alberto. Yeah, we actually have a question coming in straight away. Someone's asking, wouldn't it be simpler to get rid of Wi-Fi and go for 5G?
Yeah, okay, we can say that many people tend to see Wi-Fi and 5G as alternative technologies. The fact is that both need to coexist in order to take full advantage of the digital world we live in. It's not a matter of choosing one or another. 5G will be needed for public cellular service that covers miles and support emerging mobile technologies like, self-driving cars or asset tracking of transportation fleets or whatever. Wi-Fi is critical to provide higher bandwidth access to local area networks, and the internet in a local environment to support everything from, I would say, business application to premises-based IoT applications. We have to make one thing definitely clear. Cellular service and Wi-Fi are not the same. Wi-Fi 5 does not have any, I would say, direct relationship with 5G. Wi-Fi 5 relates to, I would say, a local area network, that's it, and will have much better performances when some hurdles or some, I would say, distributed communication is required. While 5G is just a new generation of I would say, cellular service, and so that's just a sequence in that sense. It's not a frequency.
Okay, we've actually got another one that's just come in. So you've mentioned a minimum of 25G for backbones and showed fiber links. They said that they're confused. Would this be connected to the wireless access point?
Definitely not. It's I mean, when we have a typical office environment, backbones are links which connect the floor distribution to the, let's say, the access switches in the floor distributor to the core building switch router. So that's the true backbone, typically the vertical backbone. From floor distributors, so the horizontal high-speed copper links are required between those access switches and the access point. So while we must consider at least two, as we said, two Cat6a horizontal links to provide speeds higher than 1G and up to 10 for the access point, those backbones will have to collect all the traffic coming from the distributed access point in the building and should support a minimum of 25G for the aggregated traffic. So in that sense, 25G or even higher, 50G, are supported by typically by multimode fiber backbones in duplex applications, so they can run over up to 100 meters for OM4 fibers, while 40G and 100G will be supported and are supported by current standardized applications on parallel optics, so over 8 fibers, and in that sense, again, nearly 100 meters for 50G and up to 125 for 100G in case you go for OM4. So fiber for the backbones and still considering copper for the uplinks from the access points.
Okay, excellent. There's also one more that's just come through, which says it looks like Wi-Fi 5 can run over 2.5, 5, and 10G Ethernet fixed networks. Is the existing Cat5e and 6 cabling enough for that?
Okay, that's a common question. I mean, in nearly 4 years ago, IEEE introduced a 2.5G and a 5G base T, so running over twisted pair, to potentially enable Wi-Fi 5 to the installed bases of Cat5e or Cat6. However, 2.5G or 5G are not intended to operate over the entire installed bases of Cat5e or Cat6. So, I mean, in order to check compliance to those applications, you will have to spend a lot of time. So that will require some time-consuming retesting, recertification to make sure that the application will be supported. And so anyway, to have this application running full power at 10G, Cat6a is a must. Both TIA and ISO now recommend Cat6a cabling as a minimum cabling for all new installation. So I would say only Cat6a and higher cabling systems. So we mentioned Cat6a, but we could include Cat7 or Cat7a, will fully support all the intermediate steps running up to 10G without any further need for characterization once you need that.
Okay, excellent. A couple more questions have come through. So someone's asking, why 2 links for one device?
Again, just we have seen that those uplinks now are expected to grow up to, let's say, 10G or higher, and in that sense, the management of the access points will require such a step in order to be able to support the full exploitation, the full upgrade of this. You know, in many situations, you will find a commercial device which will give you a first step of the available technology, but this is already expected to migrate to higher speed, and in order to fully support them, you will have to take this in consideration seriously. Maybe not really day one, but again, by using the scheme I showed before with a consolidation points, you will be able to connect the additional links in case you need it, and then routing the right traffic in the right directions.
Okay, excellent. Another question that's just come through was, up until now, Wi-Fi has been a complement to wired ports, although having an impact in reducing ports and ports per desk. Will Wi-Fi 6 be, in inverted commas, killer of wired ports?
I would say not at all. I mean, we've always, during all of these years, we've been facing the presence of Wi-Fi, but actually the cabling solution where always have been a growing in parallel with them. I mean, it's definitely Wi-Fi will simplify and will typically remove the very last few meters from the I would say the bandwidth availability points. That means that you do not need patch cords to connect your laptop to the outlets anymore. But as you have seen, all of you have had a chance to see how granular the distribution of those new generation Wi-Fi's is going to be. So possibly the increase of multiple devices having to run over the same networks over Wi-Fi 6 or 6E will include a a different way of designing structured cabling, so running multiple links in same areas like consolidation point or service point. But this is not expected at all to become a killer element for cable networks.